Thank you for introduction. Today I'd like to talk about, as the title says, that braid group representation of Garside's normal form theory of braid groups and some more general class of groups. So let's start. First review let us recall the definition of braid groups. Braid groups is just a group defined by this presentation, and intuitively it is easy to understand braid groups. Just we regard element of braid as geometric braids and strings intertwining and linking and so on. And in this braid picture, each generator sigma I is just I plus n strand with I and I plus first strand are positively crossing. In this talk, or in general, the generator sigma 1, the sigma n minus 1 is called standard generators. In this talk, I use slightly different but famous different set of generators and presentations as well. For I, j, n, let aij be the braid defined by this word. At first glance, this word is a bit complicated, but its geometric meaning is quite clear. It is just a braid with i's and j strand cross from above of other intermediate strands. So these braids are called band generators because it is just a boundary twisted band attached to i's and j strands. Using these band generators, braid group is presented by this in this way. Of course, you don't need to remember this presentation. Just you notice that the presentation is positive in the sense that the related always positive word is equal to positive word of band generators. So today's talk, what I'd like to talk about is a braid group. Of course, I think that many of you already hear about the braid groups and know that what is a braid group, because braid groups are related to many branches of mathematics and a lot of different interpretations. Here, I'd like to discuss the relation between two aspects of braids. First aspect is a Garside theory, which is a computational or combinatorial group theory aspect. For given braid, we have a canonical representation of braid groups as a word over the standard generator or band generators. Or one hand is combinatorial aspect, and the other side is a representation, which has various branches, which is related to various branches of mathematics, such as algebra from just an algebra or geometry or topology. So to explain the normal form, let us introduce a sub-monoid called the positive and dual positive braid monoid. It is not difficult. Just positive braid monoid, sub-monoid braid groups generated by the standard generators, which means that this is a braid which is written as a product of positive standard generators. So we are able to use sigma 1, sigma 2, but we do not allow sigma 1 inverse or sigma 2 inverse. Non-trivial fact is that this braid monoid, positive braid monoid, has the same presentation as braid groups. So as a monoid, it has exactly the same presentation. So we may abstractly view the positive braid monoid as a monoid defined by the same presentation of the braid. Then the dual braid monoid is similar. We use just, instead of standard generators, I use the band generators and consider the sub-monoid band generator. Then again the same result holds. The dual braid monoid has the same presentation as the braid group using band generators. So it is almost the same. It shares the same feature of the braid groups. So what is the Garside normal form? Garside theory is just there are various interpretations, but here I'd like to just say that Garside theory is just a theory of normal form of groups with additional structure, which is called the Garside structure. By using normal form, we are able to solve various important problems in combinatorial or algebraic group theories, such as a word problem and conjugacy problems or some other related problems. So what is additional structure? Of course, there are various formulations, but here one one definition of Garside structure is a group and sub-monoid and one particular element called Garside element that satisfies some several actions. I don't explain what is action, but important feature of these properties, but just by reviewing the case of braid groups. So the braid group case, we have two Garside structures. One is called classical and the other is called dual. For braid group, we have a classical or sometimes standard called the standard Garside structure consisting of braid groups and, I forgot plus, but say here, positive braid monoid and Garside element called delta defined by this element. Geometrically, this element called half twist, we have a strand, then string, twist string by rotating disk half pi. Key properties, which is a part of the axiom of Garside theory, Garside structure is the following. Let us consider the prefix ordering of positive braids defined by B is greater than A when B is of the form AC or C is an element of positive braid monoids. This can be written just by A inverse B is again positive braid. So we can, in some sense, we can divide B by A inside positive braid monoids. One good point is that with respect to this ordering, we have the least common multiple and greatest common divisor. The other key property is that this element, Garside element, is the least common multiple of sigma 1, that's the sigma n minus 1. So then, using these properties, we can define a normal form of braid. For braids, there exists a unique normal form sometimes called greedy normal form of the form like this. First, this is powers of delta and x1 and xn, where each xi is some special positive braid that satisfies this condition. This means that this is a divisor of Garside element delta. And this P is designed so that delta inverse P is beta is Bn plus. A key feature of the definition of the Garside normal form is that in this part, the least common multiple of consecutive product xi, x plus 1, and Garside element is xi. This means that in this representative, we take x1 as large as possible, then we take x2 as large as possible, and so on. It is not trivial, but key point is that this normal form is easy to compute. This is computed in time, length, quadratic length, and some other terms with respect to the n of the Pn. Then, using this normal form, we can solve the bad problem because this is unique normal form. So when we compute two normal forms, and then if they coincide, then two braids are equal, and if not, then these braids are different. And using normal forms and some additional operations and notions, we can also solve the contingency problem. Here's an example. Simplest example for the three braid. Three braid case, delta is 1, 2, 1, is 2, 1, 2. So by definition, 1 sigma, which appears in the definition of normal form, is here. Sorry. So sigma 1. So this is sigma 1, sigma 2, sigma 1, 2, sigma 2, 1. For example, the normal form of sigma 1 inverse sigma 2 is like this. And the normal form of 1, 1, 2, 1, 2 is by computing this, delta, sigma 2, sigma 1, sigma 1. Here's important remark. This element, the set of elements with 1 and delta is often called a permutation braid because there is a one-to-one correspondence between this set and permutation of n elements. Again, using dual Garside structure, we have a similar normal form. Instead of positive braid monoid, we use a dual positive monoid and dual Garside element defined by this element. We have a similar normal form characterized by the similar properties. So now we are positioned to describe meta theorem or motto. A theorem or meta theorem means that this is not a theorem in mathematical sense. That is somewhat motto or line or general assertion that many faithful braid group representations are related to the Garside normal form or Garside structures in a natural and direct way. I explain what is this meaning, but anyway, this means that we can read the normal form of braid from the image of representations. So even if braid group representation is not faithful, then we still have some relations, not complete, but in some cases, again, we can read the normal form of braid. Of course, it is in some sense, this assertion is trivial because if braid group representation is faithful, then schematically saying every information of braid is contained in its image, so of course it is possible to read the Garside normal form. So what is surprising and meaning, so the meaning of a natural and direct way is that we can read the normal form from image of representation in somewhat simple way. Simple and somewhat very direct way. And the second point is that in the representation we have various expressions. For example, when a representation is a linear representation, then to express a braid as a matrix, then we need to take a basis of representation, and if we take a different basis, then its image as a matrix changes. A natural means that we can read the normal form from a canonical expression of the representation. In many cases, from the construction of representation, we have natural choice of basis. And using this basis, we can represent the representation as a natural matrix. Then, from this matrix, we can immediately tell that what is a normal form of the braid. Before explaining detailed statement, why this is interesting and important. So, in general, assume that we have a faithful representation of some automorphism of some set or category or some kind of more general case of representation. Then, faithful means that this representation is injective, so we know kernel. Kernel is trivial. So, then we would like to know its image. So, it is a natural problem to determine the image. In particular, for given element of its image, then we'd like to know it is contained in the image of braid groups or not. Then, when we know that we can read the Garside normal form, then we can solve this problem. Just try to read the normal form from given element. Oh, sorry, rho x means that x. If it contains the image of braid group, then we can get a braid with image is x. Otherwise, this strategy doesn't work, so we conclude that it is not inside the image of braids. Okay, now then let us describe a more precise statement and to convince you that all braid group representations naturally and directly related to the Garside structure. To state result simple form, we just concentrate in this talk. We just concentrate our attention to the Garside length, not the normal form itself, but its length of normal form. So for the normal form, we define the Garside length in this formula. This slightly confusing maximum minimum is related to the reflects the property that P might be a positive or negative. Dual Garside length is defined similarly. This definition is designed so that this length is a geodesic length with respect to the generating set of braid groups. Then the first example is a Lawrence-Kramer-Bigelow representation. You do not need to know what is a Lawrence-Kramer-Bigelow representation. It is just a linear representation of braid groups. It is known that this representation is faithful. Indeed, the Kramer proves much more. The Lawrence-Kramer-Bigelow representation is faithful, and we can read the length of the normal form from its image. Just length is the maximal degree of its image. Here, representation has two variables t and q, and maximal degree of t and minimal degree of t. Then, so it says that variable t is related to the usual Garside length. So what is a variable q? The answer is a dual Garside length. The Lawrence-Kramer-Bigelow representation again tells the dual Garside length in the much the same similar formula. It is degree, max q degree minus minimum q degree. So it says that Garside length is just a span of the variable t and q, respectively. So, however, we need to be careful about the statement. In the theorem, to define the maximum of the image of the braid, we need to express the representation as a concrete matrix by taking a basis. One point is that from a construction of representation, we have a canonical choice of standard or canonical standard choice of basis. Then this theorem says that using this canonical choice, we can read the normal form directly. One point is that, of course, representation is faithful, so schematically we can read the normal form and length, but no technically complicated transformation is needed. We just know the image and then, okay, maximal degree is Q6 and minimal degree is Q1, so its length is 5. So it's quite easy to read. Here is another example. For quantum SL2 and its module, we have a braid group representation called the quantum representation. Again, you don't need to know how to construct this. Just you don't know that there's a representation. And such a representation is closely related to not invariant, so-called Carrot-Jones polynomials. Again, the similar situation occurs. When we take a representation generic, then it directly tells the Garside length. Here, generic means that the quantum parameter q and to define module, we take a weight, and this variable is generic in the sense it is not integer. Again, the same remark applies. This module has a natural basis in such a form generated by highest weight vectors and Then we can read the Garside length in somewhat direct way from using this basis. Finally, there's another version of another type of representation. There's a categorified bureau representation. Bureau representation is one of the most famous braid group representations. There's a categorification bureau representation. Again, I don't explain, and you don't need to know what is a categorified bureau representation. You just know there is a somewhat of categorification representation. A theorem of Kovanov and Zeidel says that a categorified bureau representation is faithful. Recently, I noticed that actually this categorified bureau representation tells a Garside length. To state results simpler, we just case the positive braid, then classical length is a maximal homological degree of the Garside length. Here B means that a certain chain complex, in the target of categorified bureau representation. Anyway, you know, this is somewhat natural choice. this says that categorified bureau representation, we know that from braid and some action on its object, then we are able to know the categorified bureau representation tells the Garside length in a similar and quite simple way. Again, the same assertion holds for the dual Garside structure. For dual Garside length, it's degree of the second degree of the image of certain image of a categorified bureau representation. Here, it is remarkable that a categorified bureau representation is faithful, but a usual bureau representation is not. It is faithful for 3, n is less than 3, and it is not faithful if n is greater than or equal to 5, and n4 case is open. Nevertheless, there is some additional, there is some relation between the bureau representation and dual Garside length. This time, it is no longer equation but an inequality. However, if n is 3, this is indeed equality, and when we assume some additional assumption on the normal form of beta, then it becomes inequality. So, still, it is not faithful representation. Still, there is a close connection between Garside's normal forms and image of bureau representation. So, in general, it is not obvious that even if representation is faithful, we can directly tell that Garside normal form. Here's one example. There is a Kontsevich invariant of braid, which is a universal representation of braid groups in this form. It is known to be faithful, but at this moment, we don't know how to recover Garside length from its image. So, in general, it is not clear that even if we have a faithful representation, it is not easy to read Garside normal form from its image, in general. And this representation point of view will be useful to attack the following problem. In this talk, I say that there is a classical Garside structure and a dual Garside structure. So one may have a question: what do you mean that? What I mean that dual? Unfortunately, the answer is quite weak. We say that the dual Garside structure because there's a quite interesting correspondence of numerical data. Here's an example. In the classical Garside structure, we use a classical Garside element. This is a product of this number of elements. On the other hand, this number is equal to the number of band generators. Conversely, the number of standard generator of classical braid, classical standard generator is n-1. On the other hand, this is equal to the length of a dual Garside element. So there is some numerical dualities. And there are more this kind of phenomenon. However, there is no clear duality at this moment in the sense that we don't know how a Garside normal form and dual Garside normal forms are related. Of course, we know if Garside normal form is given, we can try to compute dual Garside normal form and vice versa, but this is not functorial or explicit. I hope that this representation theory uses various dualities and various previous theorems indicate duality-like phenomenon. It would be useful to consider representation of braid groups to understand what is the duality in the Garside structure. Okay, the remaining 5 times, I'd like to explain how to relate Garside normal form and representation. A key point is that Garside normal form condition can be encoded by automaton or say graph and path. Say normal form sigma 1, 1, 2, 2, 2 is encoded by graph, path of this graph 1, 2, 1, 2, 2, there are various ways to write a graph. This is another different description of this graph. Again, sigma 1, sigma 1, 2, sigma 2, sigma 2. So we can encode the normal form into a graph and its path. Then the strategy is as follows. We realize the graph and its transition abstractly by using representation. Say, assume that braid group Bn acts on V. Then we decompose V into subspaces or sub-objects or some kind of, anyway, decompose our action into some smaller pieces so that when we have this transition, then transition is realized in decomposed space. Say, there's a graph, then we emulate the graph as algebraically. So when W is an element of V sigma 2, sigma 1, and when we act sigma 1, sigma 2, then sigma 2, sigma 1 is now in this space, and with degree 1 shift. So this is a kind of variant of ping-pong argument. Then the degree remembers how many times we move the graph. Degree 1, 2, 3, 4, 5, da da da. So if once this is done, we know that we are able to know degree and what is the final letter of the normal form. I skipped this to example. So this algebraic approach was taken by Kramer, Jensen, for Garside normal form, because for Garside normal form, it is closely related to classical Coxeter theory or classical representation theory, say root system or so on. So when representation has algebraic origin, then we can guess how to decompose representation, and then we are able to construct such kind of transition explicitly. However, for dual Garside case, this approach is in general very hard because of combinatorics of dual Garside structure is much complicated. So dual Garside case, we use another approach. As it is well known, braid group is identified as a mapping class group of n-punctured disk. Sigma 1 corresponds to the half twist of the disk. For a curve inside the disk, we assign the labeling in this way. First labeling is winding number labeling. Just we count the tangent vectors and we look at how many times tangent vector turns. So it winds 0 times, it has half times, it then winds 0 times. Similarly, we define wall crossing labeling, just we count algebraic crossing number of walls and curves. So 0, 1, 2, it's back to 1, da da da. So it is quite simple rule to labeling the curve. What is interesting is that these labeling of curves tells us the Garside length. So let us consider the puncture disk and horizontal line. Then consider its image and look at the labeling of its image. Then the wall crossing winding number labeling tells us the use classical Garside structure, and wall crossing labeling tells us the dual Garside length of the blades. Here's an example. This is a blade, and then it is the image. Then by looking at the labeling, its maximal labeling is 2, and minimal labeling is -2. So its length is 2 minus 2 is 4, as indicated. And this labeling has obvious topological interpretation. how many times tangent vector winds, or how many times tangent vector winds, or how many times of counting the algebraic crossing number. So it is related to the certain covering of projective tangent bundle of the punctual disk. Now, key observation is that we know that many representations are faithful, but how to prove that the representation is faithful? In many cases, the faithfulness proof of the representation, one proves that the representation detects non-trivial intersection of curves. And say, we know that, say, there is, we can detect that these two curves intersect or not. Some kind of geometric or some algebraic argument to show that representation detects a non-trivial intersection of curves, but examining its proof precisely, it actually says more. Representation actually detects the labeling of curves. For example, Bigelow's proof of faithfulness of Lorentz-Kramer-Bigelow representation says that it detects the extremal labeling of curves, and Kovanov-Zeidel proof of faithfulness of categorified Bigelow representation again tells that it detects the labeling of curves. Once this is known, once we know this observation, and together with this theorem that the labeling is related to Garside normal form, then we know that representation detects the Garside normal forms. Okay, this is the last slide. So the summary is that in many cases there is a more direct connection between the representation braids and Garside normal forms, and there are two ways to relate the representation of Garside normal form. One method is algebraic one, somewhat ping-pong argument. The other method is a geometric argument, use the labeling of curves and chase the intersection of labelings. So the remaining question is, so what is the generalization for other cases? Braid group is a special case of Artin groups, and Garside theory extends the Artin groups of spherical types, say type B, type G, type E, da da da. So there is a Garside theory for Artin groups, but currently I don't know how to use generalized labeling of curve argument for general Artin groups, because in general there is no interpretation of Artin groups as a mapping class groups. Also, the second question is that, so we know that a geometric argument from algebraic result, so translating geometric result from algebraic argument might provide a new structure on the representation of braid groups. Thank you. That's all. Thank you very much.